Oh, okay. Our next speaker is Vaidehi Paliya to talk about high energy flares of blazars.
So I'm thankful to the previous speakers for introducing the basics of Blazar. So I'll directly go to it's a well-known source 3C279. It has shown multiple gamma ray flares in last couple of years. So 3C279 is a flat spectrum quasar at redshift 0.536. It emits strong and variable radiation over the entire electromagnetic spectrum. And this is one of the first flat spectrum quasar to be detected by IGRET. And also this is the first flat spectrum quasar detected at VHE energies. And this source is a subject of various multi-wavelength campaigns since the launch of Fermi satellites. So here, this is the weakly binned gamma ray light curve of this source since the launch of Fermi. And what I'm going to cover is the three flares. First one, which came in 2013 December, denoted by OB1, that's outburst 1. Then 2014 April, and then recently this year, 2015 June. So 2013 December flare, this is the multi-wavelength light curve of the source covering the period of high activity. Top panel is the one-day binned gamma ray light curve. This is Swift XRT, second panel. Third is Swift ultraviolet. Fourth one is optical, Swift optical, as well as observations from SMARTS and stewards. And this is the IR observation from SMARTS, and these are the optical polarization measurements. So at the peak of the flare, the highest measured gamma ray flux was about 1 into 10 to the power minus 5 photons per centimeter square per second, which is typically similar to that observed by IGRET in its 1996 flare. The shortest gamma ray as well as X-ray flux doubling time scale found to be about 3 hours. And one thing everyone can notice that from the available observation, it does not look like that data at lower energy follows that what seen in gamma rays. So this suggests that this is the uncorrelated variability we have here, and this does not support the conventional one-zone leptonic model. So what we did, okay, another feature which was seen is the extremely hot gamma ray spectrum, which was seen in this during the peak of the flare, which is typically not seen from flat spectrum quasar, because FSRQs are known to be having soft gamma ray spectrum. So if we compare the shape of the optical UV, this is red data, these are the simultaneous measurements. So if you see the shape of the optical UV and compare the shape of the gamma ray, so if we consider the one-zone leptonic model to be valid, so a falling optical spectrum, this is IR to UV, a falling synchrotron spectrum should reflect in a falling gamma ray spectrum. But we are seeing a rising gamma ray spectrum. So this again gives a hint that one-zone leptonic emission scenario may fail here. So what we did here, we followed two independent approaches. If one zone is, so what we came up with that there could be two-zone leptonic emission, where IR to X-ray is coming from a relatively larger emission region, which is inside the broadline region. And the gamma ray is primarily coming from a very fast-moving small emission region. The second approach was going for the leptohydronic process. So here, actually this part was done by our collaborator Marcus Bocher. So we explained this peculiar flare with this rising gamma ray spectrum using two-zone leptonic and one-zone leptohydronic approaches. If we talk about the next 2014 gamma ray flare, same this is the multi-wavelength light curve. Unlike, the peak of the gamma ray flux amplitude was similar to that was seen in 2013 December. And here the shortest gamma ray variability was obtained about 1 hour. This is the shortest gamma ray variability was detected from 3C279. Here, unlike December 2013 flare, the flux enhancement was seen in all the wavebands, and this supports the one zone or co-spatiality of the origin of radiation. If we talk about its acidity, the beauty was that at the peak of the flare, the gamma ray spectrum was curved. a Veritas tried to observe this source during this flare, but they could not detect any significant detection. This source is a known TV emitter. That also, so what we did when we did the CD modeling of this source using one zone model, shape of the synchrotron constrained the shape of the inverse Compton. And the model which I used, that in that model the energy densities are the function of the distance of the emission region from the black hole. So fine tuning the energy density, we came up with a combination of EC from BLR and EC from torus with inclusion of Klein-Nishna mechanism. We explain the curvature in the gamma ray spectrum. And this curvature, from curvature also it suggests that there was a very less probability of detecting VHE, which was where Veritas could not find. And from the SED modeling, we constrained the emission region was located at the outer edge of the BLR. Okay, sorry. Yeah, so this SED, this is average SED, average of 7 days. So what I see, availability of good data during this flare. So what I did, I generated the final time binned SEDs. Here the same flare, but in 7 SEDs. And again I did the SED modeling to know what is the basic cause of the flare. So as can be seen that the major variation is seen only in the gamma ray band. And since we are assuming that a gamma ray is produced by the external Compton process, so the primary cause of the flare was found to be bulk Lorentz factor, because this EC variation goes as gamma square. So here what I have done, I have plotted this gamma ray flux correspond to this spectrum, and the bottom middle panel is the X-ray, and the bottom is I am showing the variation of the bulk Lorentz factor obtained from this SED modeling. As can be seen, the variation of the bulk Lorentz factor is similar to that observed in the variation in the gamma ray observations. This is the latest one, and this is the brightest flare ever observed from 3C279, where the highest measured gamma ray flux was about 4 into 10 to the power minus 5 photons per centimeter square per second. And similar to 2014 April flare, this event also showed correlated variability at different wavebands, this using the available observations. And when we talk about its SED, here also one zone model successfully explained the observations, and gamma ray spectrum showed a significant curvature similar to the 2014 April flare. And the location of the emitting region was again found to be at the outer edge of the BLR. So what we conclude from studying these 3 flares, so let's summarize. So this is what I have done here. I have plotted the SED of 3C279 taken at the peak of all the 3 flares. And for a comparison, I have taken one low activity state also. First thing, as can be seen, that dramatic changes are happening only at the gamma ray band. Most important fact is to see the 2013 December flare is the blue stars. So as can be seen here, see optical spectrum shape is not changing in any flare, but you see in 2013 December the gamma ray spectrum is rising, whereas in 2014 this red points and the black is this latest one. You see both of them are showing a curved gamma ray spectrum. So there is a change in the means the same mechanism cannot explain all the 3 flares. There is a combination of different mechanisms. So in 2 flares I was able to explain using one zone, but third flare, the 2013 December, either we need to go for 2 zone or leptohydronic process. X-ray also, you see the shape of the X-ray is more or less same, though there was a bit hardening for the 2015 flare. One other important point to notice is that 2014 April optical and 2015 June optical flux is essentially same, but you see the variation in the gamma ray band. This is it's about 1 order magnitude increase. So what I conclude, that these 3 gamma ray flares displayed the dominance of a variety of the physical processes powering the jets of 3C279. The observations reflect the complexity involved in understanding the radiative mechanisms working in the Blazar jets. And so what we need a more data. A deep multi-wavelength monitoring may reveal this kind of features, may be visible from other sources also showing similar features, but we don't have data. With deep multi-wavelength monitoring may reveal this kind of feature from other sources. Thanks.
So Vaidehi, you are assuming that the synchrotron and the gamma ray component are being produced by the exact same electron distribution.
Same population of electrons.
But it could be slightly offset from each other, right? I mean, there is no guarantee that the exact same it depends on the magnetic field values and so on. So it's not uncommon to see that actually. I guess the one that you showed at the very beginning is an extreme case of a relatively common thing that the synchrotron is in
falling and gamma ray is rising.
Yeah.
Could be.
Hello. So if you could just go back to the slide. Yeah. So if I just extend these black and red lines, they would. I'd assume that they would smoothly extend into these other gamma ray flares.
You see this one?
Yeah.
Actually, here X-ray is primarily from synchrotron self-Compton. These green dashed lines I should have told. Synchrotron is this optical UV synchrotron. X-ray I'm explaining from synchrotron self-Compton, and gamma ray primarily external Compton. So ultimately, see the combination of all the mechanisms will give you the observations.
Yeah, but you're claiming that it's different for the gamma ray flares. I'm saying that if you just okay, I think we can discuss it later.
Yeah, we have another question in the back here.
So is there any physical reasoning behind why leptohadronic model is working for the 2013 flare, whereas leptonic models are working for other flares? Because what is happening to hadrons at that time then? I mean, they can't just suddenly decide to not contribute to radiation.
I just have no idea. Means in one flare only its effect was seen, and other two flares it's gone. The rising spectrum, see this a rising gamma ray spectrum demands
No,
additional
I understand
mechanism.
that it has to do with
Something, yes.
modeling the SED, but I'm just talking about like once you've modeled the SED, then what is the physical reasoning behind why a leptohadronic is applicable in one and not in others? And then what is happening to hadrons at that time? I mean, it was just, anyone can comment on that.
You have a comment on the question?
To respond maybe to that, adding a hadronic component will add an extra free parameter. So if the model doesn't fit, basically, adding an extra zone or adding an extra hadronic component's presumably what they did. It doesn't look like it fits very well either.
Quite hear you there. You're saying an added extra component. The hadronic model adds extra parameters.
Yeah.
And so it's easier to fit a more complicated model?
Yeah, if your one zone model doesn't describe the flare well, then you can add extra, you just complicate it until it does. So add an extra hadronic component. And then it doesn't appear in others because the one zone model works for those.
Two-zone or multi-zone, right? I mean, fine, that you can still physically understand. But to go from a leptonic to a leptohadronic, that is, I mean, I'm just talking about physically, how do you justify that? That's the only, I'm not saying that the modeling is wrong.
No. I don't think models are very physically justified anyway, right? They're just separate blobs that have been added. I think you could just add an extra leptonic zone and fit that extra peak with leptons as well. Yeah. It would probably make more sense.
I just has a quick comment. I was expecting Manisvita to point it out, but she showed yesterday that the oblicity of magnetic field, with that we could also expect a lot of variations in the high energy spectrum and absolutely no variation in the low energy spectrum. So maybe that could add something. I'm not an expert on that. Maybe she could point it out.
Maybe, but I'm not getting what.
If you take magnetic field, and can you explain the spectrum? I mean, have you tried or had anybody tried that?
Sorry?
This is a discussion. I think we are heading into a discussion now.
I handled it in the break, which